Now, the next step on our journey in terms of functions is looking at what we call composite functions. Now, the word composite means composed of, okay? So it's usual to say that every function that exists normally can be decomposed into smaller functions, okay? Now, just to give you an example of that, take a look at this. Take a look at the function p of x equals x squared plus 5. If I was to ask you, what is p of 3? What would you do? So take a moment to think, how would I find p of 3? Now, obviously, what you'd say, and being trained very well from your junior cert, is that 3 goes in where x is, it's squared, and then you add 5. Okay, perfect. And that's exactly what you would do, because when you square 3, you get 9, and when you add on 5, you get 14. So therefore, you'd say straight away, without much of a thought, that the answer would be 14. But I want you to think carefully about the function you've just used. You tackled that function in 2 steps. The very first thing you did was you squared 3, you got your 9 in your head, and then you added on 5. So in other words, we can see that p of x is in fact 2-stage process. Okay, so think of it again. If you described it properly, as I've just done there, and I'm sure the rest of you did as well, you would have said the following. The very first thing we do is we square 3, we get the 9. Okay, we hold the 9 and then we add on the 5, and that's where we get our 14. So what was a single function has now been broken down or decomposed into 2 steps. And what we say is that the original function x squared plus 5 is composed of 2 smaller functions. And in fact, the functions are the actions that you mathematically do. So you square the 3, that's the first step. Then you add on 5, that's the second step. So therefore, what was the function p of x equals x squared plus 5 is in fact made up of 2 smaller steps, squaring a number, in this case 3, and then adding on 5. Okay, so that's what we say. The original function is therefore said to be composed of 2 simpler functions, or 2 smaller, what I like to call, steps, because the simpler functions are actually the steps involved in getting the answer. It's what you do with the number that you're inputting into the function in order to get your output. Or put another way, to use the language you're used to, it's what you do to the domain value in order to get the range value. Okay, so these 2 simpler functions could be written as the following. You could write them down as g of x and, of course, h of x. Now, again, I want to point out that functions in their own right all have to have a name, and the name we give a function is simply a small case letter. So the original function was p, and inside p we discovered that we were going to square 3 and add on 5. So the act of squaring itself can be given a name, g of x, and the exercise of adding on 5 can be given h of x. Now what you will notice is that even though p of x was equal to x squared plus 5, the first part, the x squared, becomes g of x. It gets its own name, okay? And when we get the answer, we then reset the function, so to speak. We go down and we say that we're now going to add on 5 to the answer. But do you notice that the answer has been reset to x? So put it this way, p of x equals x squared plus 5. Take p of 3, as we already did a moment ago. P of 3 is equal to 3 squared plus 5. So the x squared part is the first function, and when we get 9, we then call 9 the new x, onto which we are going to add the 5. Okay, so we don't carry on the x squared down through the simpler functions. We just state clearly what we're doing in each step, and for each step, the number that you're using is going to be referred to as x. Okay, and the result is found by what we say doing h of x after g of x. And let me just clear that up there, and I'll show you what I mean by that. So p of x was what? P of x was x squared plus 5. Now, what did we do first when we wanted to get p of 3? Didn't we square first and then add on 5? Okay, so in other words, if I was to explain what I did in English, isn't it true to say that we added on the 5 after we squared the 3? Okay, think about that. So in other words, when you're taking your steps, you're doing one step after the other. And in this case here, you're adding on 5 after you square the 3. All right, so you square the 3 and you get 9, you add on the 5 and you get your 14. Okay, so that word after is extremely important because we have to decompose a large function into smaller functions or simpler steps, and each one of those steps is done one after the other, and that word after gives us the method and the procedure, I suppose, in which we carry forward our answers. Okay, now when we're using the word after, every good mathematician knows that we don't like words, we prefer symbols. Okay, so the symbol for after is a very simple small o. Now it's not the degree symbol up high, it's down between the h and the g at the bottom. Okay, and I'll show you what it looks like, just like that. Okay, so this is written as h after g of x, or h after g of x, or just h after g of x. So even though it has its own little symbol, that little symbol is not necessary. It doesn't have to be in there. If you have the two letters of the two simpler functions that you're going to use, you always read them as h after g. Now think about that. If it's h after g, who do I do first? H comes after g. So doesn't that mean that you work out g of x first of all, and then you feed it back into whatever the function h tells you to do? Okay, so g of x will give you one answer, then you take that answer back into h of x because you're told to do h after g. All right, now the examples will make this a little bit clearer as we go along. So the function that contains the bracketed x is the one that's always worked out first. And again, if you go back up here, look, h after g of x. G has the bracketed x. That's worked out first, and then the answer to that is fed into the function h. So let's do this up here. Taking 3, and we're going to do what? H after g. So that means we're going to put 3 in here first to get 9. And then we're going to take the 9 down here, and we're going to add on 5 in order to get 14. Okay, so that's the essence of composite functions. They're the smaller steps in a large function that allow us one after the other to get to the final answer. So let's take a look at this one here. And again, examples always mean more than just words. F of x is 6x plus 2 and g of x is x squared. Both of these functions use the real numbers as their domain and the real numbers as their codomain. So in other words, the numbers I'm going to be plugging in are going to come from the real set, and all possible solutions are going to come from the real set. Okay, that's just what those two ors mean. So that's your domain and that's your codomain. Find the value of f after g of x. Now, think about that. Find the value of f after g of x. Now, what does that exactly mean? It means that you're going to take g of x and you're going to put g of x into f. Now be very, very careful how you do this. Find the value of f after g of x. G of x, which is x squared, is going to be carried in its entirety back into f wherever x is in f, so to speak. All right. So in that situation there, what am I going to get? I'm going to get 6x squared plus 2, which would be the major function from which both f and g are the smaller steps. Okay, try the next one. Find the value of g after f of x. Again, because the f has the bracketed x, we're going to take f of x, which this time is 6x plus 2, and we're going to place the entire 6x plus 2 in where x is in g. And what that gives me is 6x plus 2 to be squared, which of course you all know is a binomial expansion, which you can do because we did it at the start of the book, is 36x squared. 2 6s are 12 and double the result, 24x plus 4. And then the question down here, part 3, says, is f after g of x and g after f of x commutative? Now, look, all mathematicians need to know their vocabulary, okay? Commutative means that no matter what way you use f and g, you're going to get the same answer. So if f after g of x and g after f of x were commutative, then the answers that would come out when you've worked them out would be exactly the same. Here, it's clear to see that 6x squared plus 2 is not the same, obviously, as 36x squared plus 24x plus 4. So the answer is they are not commutative. And please do remember that word going forward. Commutative means that no matter what way we put g into f or f into g, the answer comes out the same. That's not the case here. When we put g into f, we got 6x squared plus 2. And when we put f into g, we got 36x squared plus 24x plus 4. So the outcome is completely different. Now, let's take an example of f after g of 3. So let's take an actual value. What does this tell me to do? First of all, the 3 is placed into g, okay? Because you only do f after you do g. So you place 3 into g. What does that give me? We'll go up here to the function. If I take 3 and put 3 into the function g of x, I'm going to get 9, okay? And then I carry that 9 all the way back into the function f. So therefore, the first step would be g of 3, and g of 3 is equal to 9. So we're now going to carry that 9 into f, which means we're going to place 9 into 6x plus 2 to give me 6 9s plus 2, which is 56. 6 9s is 54, and 2 is 56. Okay, what about this one? G after f of 2. Now again, let's do f of 2 first, because that's what we're told to do. You always take the 2 into f first of all. So you're going to place 2 into f. Go back up here and put 2 in where x is. 6 2s are 12 plus 2, 14. And then after you do g, okay? So therefore now you're going to take the 14 into g. And g of 14 is going to be, take the 14 back to the g function, which means you're going to square the 14 to get 196. So it's painfully obvious to see mathematically too, using values, that they are not commutative, okay? And even though we're using different values, you can see there also appear that they are certainly not commutative. Okay, so that's how we work out these values, these what we call composite functions. The smaller ones will be given, but just be very careful with the order, because the one that contains the bracketed value is the one that's always done first. And when you get an answer to that part, then you feed that answer back into the previous one, which, as the question tells you, is done after you work out the one that contains the bracketed value. Okay, let's move on. Now, let's take this one here. H of x equals x plus 1, g of x equals x squared, and f of x equals x minus 2. So you've got 3 functions, h, g, and f. And I'm only going to do part 1 and 4 of this question here, page 132, question 15. Find f after g of x, then find g after h after f of x. So they can be what we would call triply composite, but that's perfectly fine. Just keep your head, focus, slow down, take a deep breath, and take it step by step by step. So let's do the first one. Find f after g of x. Now, it's g that has the bracketed x. So that's my starting point. And what I'm going to do with g of x is I'm going to carry it back into f. Okay? Now, because it's g of x, you've got to carry g back with its x's into f. So likewise, I'm going to take this one here and I'm going to bring it back into this position. Sorry, it's f of g of x. Apologies, f of g of x. Let me try that again. So it's f after g of x. So you're going to take g of x back into f, which means taking g into f where x is. Do you see that? So now you're going to put x squared in that position. And what are you going to end up with? X squared minus 2. Okay? Take the second one. G after h after f of x. Now again, you always begin with the term that has the bracketed x or the bracketed value. So in this case, let me just erase the arrows from above. Let me just take these off here because I need to use that again. So this time, I'm going to first of all take f of x. I'm going to start with this, and feed it back into what? Well, I'm going to first of all feed it back into h. Okay, so let's just see first of all, what does this become? When I take x minus 2 and I bring it all the way back to h, where x is, what does it become? Well, the x minus 2 goes in there where x is, and it becomes x minus 2 plus 1, which is x minus 1. Okay, so once I've worked out what happens to f of x when it goes into h, I'm now going to take the result of that and feed that into g. So now I've got to take x minus 1 into g. What does the function g do? It squares anything that is inputted into it. So I'm going to input x minus 1 into g, which means that the x minus 1 is going to be squared. And again, it's a binomial, so it's x squared minus 2x plus 1. And that's the result of the triple composition. Okay, so it's quite easy, but I would say, look, work them out step by step. Start at f of x, which is x minus 2, bring x minus 2 into h, so you bring x minus 2 into h and you put it in where x is with brackets, okay? The original x in the h is not going to be there anymore. It's going to be replaced by x minus 2. So it becomes x minus 2 plus 1, which becomes x minus 1. And once you've worked out that part, you now take the value of that back. That goes back into g. So you're going to take the x minus 1 into g, which is this function here. And what does g tell you to do? Square whatever you've just received by putting f into h. So I'm going to square this one, okay? And x minus 1 to be squared being a binomial. You square the first to get x squared. You square the last one to get plus 1. You multiply these two together and double the result for the middle, which is minus 2. Okay. Next one. Given that f of x equals 3x plus 1 and g of x equals 5x plus c, find c if these two compositions are commutative. Did you hear my language? If f after g of x equals g after f of x. Now again, if you change the order of the functions and the answer comes out the same, then we can say yes, in this case f and g are commutative functions, okay? Or commutative compositions, I should say. So let's work out the first one. F after g of x. Starting with the bracketed one, you're going to feed g of x into f. So I'm going to feed g of x into f, exactly where x is. So what's that going to give me? 3 times 5x plus c. Do you see the way I've replaced the x completely with the contents of g of x? Okay, plus 1. And that's to be equal to g of f of x, or g after f of x. So now I'm going to take f of x and put it into g. So now I've got to do it this way. I've got to take the f of x there, and I've got to feed that into g, wherever x is there. And that becomes 5 times 3x plus 1 plus c. Now notice, and this is something we did in algebra at the very beginning, that c is the only variable present. So this can be solved for c. So let's do what the brackets tell us to do. 15x plus 3c plus 1 is equal to 15x plus 5 plus c. Do you see that? So 3 5s are 15. 15x plus 3c plus 1 equals 15x plus 5 plus c. All right. Now the lovely thing here is, of course, because 15x is the same value on both sides, it cancels. So now you gather your variables to one side and your constants to the other side. So that means we're going to get rid of plus c by introducing a minus c on both sides. So 2c is equal to 5 minus 1, which is 4, and c, therefore, is equal to 2. Do you see again how reliant we are on the algebraic chapters 1, 2, and 3 from book 1? You must keep those at the forefront of your head going forward. Keep revising them, because they do come up. I promise you, they come up everywhere, all the time. Okay, over to you. I'm going to leave you now with page 132, question 15, except for parts 1 and 4, which I've already done in the previous example, then question 17, and then turn on to page 133, and off you go with 20, 21, 23, 24. So you can pause this video now, go away and do those particular sums, and in the next section, I'm going to bring you through graph drawing, okay? Okay, so In the next section, we're looking at linear and quadratic functions. Now, I do need to take a little bit of vocabulary here. I do need to take a look and see, do you understand what linear functions are? Do you understand what quadratic functions are? Linear, if you just look at the word linear, I-N-E-A-R, if you drop the last two letters, what do you get? Let me just erase that. If you drop the last two letters, you get a line. So therefore, linear functions are always functions that will end up giving me a line as a result. See that? Okay. Quadratic functions, something again which we should be used to from your junior cert, are those functions that give you the U-shaped or the N-shaped, depending on whether we're dealing with x squared or minus x squared. And again, that's something coming from your junior cert that I would ask you to remember. If the initial term, if the squared term is positive, your graph will be U-shaped, but if your squared term is negative, your quadratic function will be N-shaped. And really what I want to do in this section is nothing more than just remind you of how to draw graphs, okay? And to draw graphs, you've got to need graph paper. Don't try to do these on anything else except graph paper. That's the most important thing. And second to that, use the full sheet. Don't have a little graph up at the top. Don't have a situation like this where you've got a big sheet of graph paper and your graph is up here like that. Okay, what a waste of space. What you should always strive to do is to make sure that you utilize the full page as best you can. So there's your graph like this. There's the values we're going to be using, and we get a graph like that. Lovely. And then we get maybe a linear one in with that. Use the full page. Okay. Secondly, always label your axis. Okay. And thirdly, please, please, please do your best to graph these as accurately as possible. The word graph means accuracy is important. Okay. You'll be very surprised to know that if 10 marks were going for drawing a graph, maybe 3 might go for your graph and 7 go for something else. 7 go for the table of XY values. See that? So you've got your X and your Y values like that. Say 1, 2, 3, 4, whatever it's going to be, and then whatever your values, blah, 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 down here. Now, your calculator will be invaluable. Calculator, can't even spell anymore. Your calculator is invaluable because your calculator generates the table. But even though your calculator generates a lovely table, your table must be presented beside your graph or on the same page of your graph. The examiner has to know where you got your points from. Okay, so even though you can generate it here, please don't. I mean, don't just leave it there. Take it from the screen, your calculator, and put it into your copy so I can see the values of the points that you're actually plotting. Okay, so 7 marks for your table, 3 marks for your graph itself. Now, I might be exaggerating a little bit. It might be more 4, 6 rather than 7, 3. But at the same time, there has been occasions when the table has got huge values and the graph has practically got very little. Because if you can generate the values, at this stage, they think doing honours maths, you're going to be able to draw a graph. Okay, so that's just a little aside before we begin. Now, here's what we do know. A linear function is a function of first degree. All right, now we had this before. First degree equations contain x to the power of 1. All right, now we don't ever write down x to the power of 1 because 1 is the power that generates every term itself. So x to the 1 is just written as x. Secondly, a quadratic function is a function of second degree, okay, which contains an x squared. So for example, something like this, 4x squared minus 7x plus 2. I can describe that straight away as two things. It's going to be U-shaped and it's a second degree function. All right. And lastly then, a cubic function of third degree will always contain some type of x cubed and will result in a graph that turns twice. So a linear function is of first degree, like that. A quadratic function of second degree will turn this way or this way, depending on whether the x squared is negative or positive. All right. And finally, a cubic function of third degree will always contain x cubed and will either be like this or like this. One or the other. Okay, so keep those please in mind because they are the functions that we're going to be focusing on as we go forward in graph drawing. And an example of a cubic function would simply be minus 2x cubed plus 2x squared minus 3x minus 9. All right, so straight into the example because I want you to get you to start to draw some graphs using the same scales and the same axes. Now, when they say that, what they mean is that you're going to place both of these functions onto the same graph. They must be drawn together. So same scales and same graph, or same axis I should say, simply means please put them together on the same page. Okay? And graph. The word graph is extremely important because the word graph means that they must be accurate. They have to be accurately drawn. No sloppy work. No just around with your pencil like that. You've got to sketch them very carefully to make sure that they take in all the points you've plotted and that they turn properly. Okay? Because the more accurate your graphs are, the more accurate your answers are going to be. So in this case, they want me to look at g of x, which is minus x squared plus 6x, and h of x, which is 2 over 3x plus 1, from the domain 0 to 6. Now, this is extremely important. The domain, if you remember back to Monday's class, is all the x values I'm going to use. So in a situation like this, there will be no need for me to use any negative x values. So you're not going to divide your page up like that, for the very simple reason that you don't need that axis. You're not going to be using negative x values. So you're only going to be using values between 0 and 6, which means when you draw out your page, you should be doing something like this. All the x values there. Okay, and then let's see what happens with the y value. So I'm not too sure where to place the x yet. So you generate your table, and you're going to generate your table first. Okay, and then we'll come back and do those questions in a moment. Okay, so generate your table, and there it is. Now your calculator does this quite well for you if you use the alpha x. If you're not too sure how to do the alpha x, if you can't remember, please get back to me, send me an email, and I'll do a little video maybe on how to use the alpha x on the calculator. Okay, but you use the alpha x with 0, 1, 2, 3, 4, 5, and 6, and the first function, this one here, generates these values. So therefore, they are a set of couples that will generate what g of x looks like. Okay, and likewise, you can also do h of x between 1 and 0 and 6, and they're the values over there that they give me. So therefore, those two sets of values will draw h of x, okay? And then these two sets of values here will draw g of x. Now, it's perfectly okay to put them all on the same table. After all, you're using the same x values, you're just generating a different set of outputs or a different range for each of these functions, g of x and h of x. So when I plot these, and thank God I have the wonders of modern technology here, so you won't see how I sketch anything, I'll get the computer to do it for me. What do they actually look like? Well, when I generate them and I plot them properly, that's what you should get. And your graphs should be, or close to, as accurate as what you see there. But you notice your x and y axis. Your x-axis starts at 0 and runs out to 6, and your y-axis goes from 0 to 10. Do you notice on this page there's no wasted space? I didn't include any negative x values, and I certainly didn't include any negative y values because I don't need them. If you go back to the table we had a minute ago, what do we notice? That my x values go from 0 to 6, so there's 0 to 6, and my y values for both graphs are all positive. So therefore, the only thing I need on my page is a positive x-axis and a positive y-axis, and that's perfectly enough to take in my graph. So don't go wasting space dividing your page up into 4, because you might need 2 or 3 of the quadrants that are actually there. Okay, so that's what the graph looks like. There it is. Oops, there. Now, I'm going to squash this in a little bit, and I'm going to try and answer the questions with you as we go along, because normally when you've sketched the graph, don't forget, that's x and that's y. Now, you do have to make sure that you label your axis. Please, 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 for God's sake, always label your axis, because they will take marks off if you don't. Otherwise, we don't know what you're comparing, what two values you're comparing. Here you're comparing x's with y's, so we know that you're comparing inputs with outputs, or, put it another way, a domain with a range. Okay, so what are the questions? Use your graph, and this means that you've got to show evidence on of your graph of being able to work with it, okay, to estimate the values of x. Now that's important. Estimate the values of x. That means that all your answers are going to come from the x-axis, okay? So that's extremely important. They're values of x, for which, number 1, g of x equals 5.5. Now, if g of x is the function, then obviously 5.5 must be the output, and the output is a range value which is always found on the y-axis. So what they're asking me to do here is to find the output 5.5, and now again, I don't have to divide up as well as I can, as well as I should have. So there's 5, there's 5.5, okay? So there's the output 5.5, and what it's asking me is, what values must I plug into my function to give that output? So what I would suggest you simply do is you draw a line. Now you'd use a ruler, I haven't got one here, but you'll draw a line straight through 5.5 and find out where it cuts the graph. So you'll notice it cuts the graph here and it cuts the graph here. And what you do, because the answer wants the values of x, is you will immediately drop down like that onto the x-axis to try and figure out exactly what the answer is going to be. And likewise here, the same thing. You drop down your answer. Now you would have done something like this for your junior cert anyway, so this is nothing new. So there's your first answer, and there's your second answer, okay? So what answers do I have? Well, x is equal to, in this case, what have we got? It's about minus 1.1. Now sorry, every time I bring the pen close to this thing, it seems to bring up a little menu. So that's 1.2, 4, 6, 8, yeah. So it's about 1.1. 1.1, and there's a second value, which is over here, which is 4.9, roughly 4.9. Now, don't worry if your answers aren't exactly the same as mine, because there's a margin of error given. They know that people are drawing these freehands, so they give a margin of error to allow for a certain number of decimal points either side of the actual answer. So don't worry about that. So that's the first one. Okay. Second one, let me just get rid of those. Second question. H of x equals 3.5. Now, h happens to be the line. See that? G of x is the curve, and h of x is the line. So now they're trying to find out where the line function gives me an output of 3.5. Well, first of all, the h of x is giving me an output, a range value of 3.5. So I find 3.5 on my output axis, my y-axis, and I draw across. But this time, I'm interested in where that 3.5 line cuts h of x, which is the blue function, this one here. And again, I drop down like so, and I notice in this case that it's very, very close to 3.8. Okay, so just be careful that you understand what function you're dealing with. The g of x is the arch, and the h of x is the line. So where is the arch giving me out 5.5? That's why I went to 5.5 and drew and got these two answers here. Where is h of x? Where's the line giving me an output of 3.5? So I go to 3.5 and I draw towards the line. So be careful you're using the correct function in each of those. Okay, let's take that off there. Third one. Where is g of x equals h of x? Now, remember what I told you. G of x is the curve, and h of x is the line. So you're quite free to replace g of x and h of x with the words curve and line. Where is the curve equal to the line? And the answer is there and there. So all again you've got to do, remember you're looking for the values of x, is to drop down onto the x-axis like so. Now, apologies for my diagrams here, because I'm using a computer screen to draw on, which is quite hard. So there's your first answer. There will be your second one. Okay, so in this case, what do we notice? The answer is that the line on the circle, actually the line on the circle, sorry, I'm going to just take that off there because it's too close. Let's see if I can do it again. Okay, so it's there. That's a bit better. Okay, so the line and the arch are here at an answer of 0.2 on the x-axis. So if you drop that down there like so, okay. And the second answer here, where the line and the arch are the same, is roughly, it's nearly 5.2. And you're safe enough to say that within a certain margin of error to get that answer. So there's your two answers to that one. Now, where is 2 over 3x minus 1 equal to 0? Now, in a situation like that, and I've got a star beside this, because you'll notice 2 over 3x minus 1 is not any of my original functions. It's not g of x and it's not h of x. So what I have to do here is I have to take 2 over 3x minus 1 and turn it into an x value. Okay, so in other words, let's see what we can do in terms of rearranging this equation. So I'll get 2 over 3x equals 1. I'll get x equals, now don't forget how to clear the fraction. You're going to divide by 2 and multiply by 3. So it becomes 3 over 2 times 1, which is 3 over 2. Finished. Nothing to do with the graph whatsoever, because it wasn't one of your original functions. So you're quite free in a situation like that in order to show that by rearranging the equation, you can work out exactly the value of x that you're looking for. And the value of x in that case is nothing more than 3 over 2. Okay, the next one. Where is g of x greater than or equal to h of x? Now, in a situation like that, g of x, as we told you already, and I keep writing this down, g of x is the curve and h of x is the line. And what this is asking me is, where is the curve greater or equal to the line? And it's painfully easy to see that between that point and that point, the curve is far greater than the line. So therefore, we'll simply say that the answer to this is between. Okay, x equals, now it's between. So all of those values in there, the curve is greater than the line for all of those x values. So you can say, look, you could drop that down there if you wanted to, like so, and you can say between there and there. They're the values inside which the curve is greater than the line, meaning the curve is above the line. Okay, and what are those values? Well, we had them earlier on. Between x equals 0.2 and x equals 5.2. So between those two x values there, that one and that one, we notice that the curve is above the line or greater than the line. Now, if the sign was the other way, that way, you'd be looking for something that's below the line. Okay, but in this case here, they're asking you for what is above the line. So therefore, the curve is above the line between that point and that point. And because you have to use your x-axis, you drop the 2 points down onto the x-axis, and they are the two values between which the curve is greater than the line. And finally, just one more here. Where is the g of x a maximum? Now, the function, what does the function do? It spits out values. So what they're asking you here is, where is g of x? Where is the curve at a maximum? And if you follow the curve is at a maximum here. So what they're asking you is, what value of x causes the curve to have a maximum output? And the answer is, if we follow it straight the way down there, the answer is x equals 3. Now, most of that you would have done already for your junior cert. The practice I want you to get into is how to draw these graphs and make sure you draw them properly. All right, here's another one. Graph the function of f of x equals x squared minus 2x minus 5 in the domain minus 2 to 4 and estimate from your graph the following values. Now, I already have this graph drawn. You would have to draw this yourselves. I have it drawn like so. So I'm going to just tackle the questions, okay? And again, notice we're using minus 2 to 4. So there's minus 2 to 4. I'm only using the x values that I have to use. And when I generate my table, as you will do, the following graph will be plotted. Okay, estimate from your graph the value of f of 2.2. Now, what do you notice? You notice here that 2.2 is in f. That 2.2 is an input. Okay, so therefore 2.2 is an x value. So in that case, to work out 2.2, well, there's 3 for a start. So that's 2.5. So 2.2 is roughly there. Okay, and I say roughly because I haven't got graph paper that allows me to see 2.2. So what I'm going to do, and it says estimate from your graph, I'm simply going to drop this down until I hit the graph like so. And then I'm going to run across here to get my output. And my output is roughly 4.5. Well, maybe minus 4.4 or thereabouts. Okay, so y equals minus 4.4. That's the answer. So again, what did I do? 2.2 is in the brackets, therefore 2.2 is an input. So you're going to take 2.2 into f, which means you're going to bring 2.2 on the x-axis down to the function. Then you're going to hit the function there, and you're going to turn 90 degrees to get the answer or the output from the y-axis, which is roughly about minus 4.4. Okay, part 2. Find the values of x for which x squared minus 2x minus 5 is equal to 0. Now, if you have your eyes in properly, you'll notice that that is exactly the same as the function. So what they're asking you is, where is f of x equal to 0? In other words, where does x give an output of 0? Well, there's the output of 0. So the values of x that give an output of 0 on this graph are this one and this one. You simply go to the output 0 and you draw across until you hit the arms of your graph. And here we notice that this is 3.5 exactly, and this one here is minus 1.5. So in that one, x equals 3.5 and minus 1.5. And finally then, the values of x for which x squared minus 2x minus 5 less than or equal to 0. So again, you'll notice that is the same function as what we had before, f of x. So what they're asking you is, and f of x, by the way, is the curve, yeah? So they're asking you, where's the curve less than or equal to 0? Well, the curve is less than or equal to 0 between those two values we found in the previous part. So the curve goes below 0 all the way through to there. So from minus 1.5 all the way across to 3.5. So what I would be inclined to say for the answer to this one is the words between. So just be careful you put that in, because all the values between minus 1.5 and 3.5 bring that curve below the x-axis. So it's between minus 1.5 and 3.5 on the x-axis. Or another way to say it, between x equals minus 1.5 and x equals 3.5. And finally then, part 4, the minimum value of f of x, the minimum value of the curve, the lowest point on the curve. Well, the lowest point on the curve is there, right? So the lowest point in the curve is here. I can't get down that far. The lowest point in the curve is down here, and they want the values of x. So you go to the lowest point, which is this way. Let me do it this way. Which is there, and then you simply draw up to the x value. So go to the lowest point, draw up, and you'll notice exactly that part 4 is, the answer is x equals 1. And lastly then, use an algebraic method to find the exact solutions to the equation given in part 2. Now look at what part 2 is. Part 2 is x squared minus 2x minus 5 equals 0. It's a quadratic equation. Solve it as normal. Open up your brackets. See if we can work it out this way. Okay, x by x. So factors of 5 with a difference of 2 between them. Factors of 5 with a difference of 2 between them. There's none. 5 is prime. So therefore use your minus b formula. Okay, so x squared minus 2x minus 5 equals 0. Use your minus b. Minus b plus or minus the square root of b squared minus 4ac all over 2a. And fill in your values. Minus minus 2 is plus 2. Plus or minus minus 2 squared is 4. Minus 2 times 1 times minus 5 all over 2 times 1. And the two answers that come out from that is as follows. Get your calculator. That should be the same as what I got already. So you've got 2, so you turn on your fraction. Whoops, and don't forget to go back into normal mode, which is shift 1. So you have 2 plus the square root of 4. Now, minus 2 times minus 5 is plus 10. So that's 14 all over 2. And the answer there comes out as 2.87 for the first one, which wasn't too far away from what I got. And then the second one, if I have change the plus for a minus, the second answer comes out as minus 0.87. Okay, so they're the answers we get to this one up here. Okay, so minus, there's again minus 2, in case you wonder where I get these figures from. There's a, b, and c. So minus b is plus 2, plus or minus b squared, minus 4 times a times c, all over 2 times a. All right, so you've proved mathematically the exact solutions to the equation, which is quadratic, in part 2. Okay, final one before I give you some to do yourselves. Use the same scales and same axes, again put them on the same page, to draw the graphs of the two functions f of x and g of x in the domain from -3 to 2, and x will involve all real numbers. Now again, thanks to the wonders of modern technology, there's the graphs we're dealing with. So you can see the part of the quadrant that we're dealing with here. And they want me to use my graph to estimate the values of x for which f of x equals g of x. Now be careful. F of x equals a positive quadratic. So that's going to be U-shaped. G of x involves a negative quadratic, which is going to be n-shaped. So in other words, what I could say here, when they're asking me to get f of x equals g of x, is I could simply say where the U-shape is equal to the n-shape. See that? Now, where is the U-shape equal to the n-shape? Well, there and there. That's where they're both equal. And they want values, where are we now? Yeah, values of x. So in other words, find out where they're equal and drop down onto the axis. There we go, there and there. Now, what do I get? I end up getting 0.6. So for that answer there, for part 1, x equals, and over here, minus 2.6, and from over here, 0.6. And then lastly, part 2, use your graph to estimate the values of x for which f of x is greater than or equal to g of x. F of x greater than or equal to g of x. Now, how do I do that? Well, f of x is the U-shape greater than or equal to g of x, which is the n-shape. Now, where's the U-shape greater than the n-shape? Well, obviously here and here. That's where the U-shape is greater than or above the n-shape, okay? Because it's outside it. So in that situation, what we've got to remember is that the arms of a graph go off forever, okay? So the very first thing I've got to notice here is that this part of the U-shaped curve will go from -infinity all the way up to -2.6. So there's the first set. And it will, this arm here goes from 0.6 up to plus infinity. So in other words, what you're saying is that the arms of the U-shape are greater than the turn in the n-shape, where we see the arms going off to infinity. This one here, as I have in red, and this one here that I haven't read. So those less than, greater than, less than, equal to, greater than, equal to signs, they're just asking you about where one part of the graph is either above or below the other part of the graph. And when you've got an equal sign, as we had in part 1, that's where they intersect. So that, f of x equals g of x, is what we would call a point of intersection. Okay, look, I'm going to leave you with these questions to do now yourselves, but here's what I want you to remember. The most important part of any graph is the table of couples. You must generate it and write it down, okay? By all means, use your calculator, but draw the table in to attain full marks, all right? Secondly, I want you to graph carefully. Make sure it's accurate onto a full sheet of graph paper. Okay, and there's the questions that I'm going to leave you with. Page 138, questions 6, 7, 8, 10, and 12. Now, hopefully, I'm hoping to have a live class on, where's 50 year maths? A live class tomorrow, Friday. And that's where I'm going to take your questions and go through questions with you that maybe you didn't get the first time round, okay? But do your best, work on the composite functions, work on the graphs, and we will have a live class on Friday to get through those solutions.